Section 5.8, Absolute Entropies, and the Third Law of Thermodynamics. The third law states that the entropy of a pure, perfectly crystalline substance is zero at 0K. For example, at 0K, oxygen is a solid crystal. Its entropy is exactly zero. Given this information, and also given the heat capacity of oxygen solid, oxygen liquid, and oxygen gas, also given the enthalpy of fusion and enthalpy of vaporization of oxygen, we will be able to calculate the entropy of oxygen gas at any temperature, for example, the room temperature. How do we do that? Well, we simply calculate the difference between the entropy of oxygen gas at the room temperature and the entropy of oxygen crystal at 0K. So we know this is zero. That's from the third law of thermodynamics. And then, because enthalpy is a state function, we can gradually increase the temperature of the oxygen solid from 0K to its melting point. And then we can use this equation to compute the entropy increase from 0K to the melting point, while this oxygen is in the solid phase. This term helps us to calculate the entropy change of the fusion of the oxygen. After that, we have oxygen liquid, and then we calculate the entropy increase of the oxygen liquid from its melting point to its boiling point. Between these two temperatures, this oxygen is in the liquid phase. At the boiling point, we can compute the entropy change of this oxygen by using the enthalpy of vaporization divided by the boiling point. Finally, between the boiling point of oxygen and the target temperature, let's say the room temperature, we can integrate this Cp dt over T for oxygen gas. So this way, we will be able to compute the entropy of oxygen gas given the third law of thermodynamics, given this Cp of solid, liquid, and gas. Also given this enthalpy of fusion and enthalpy of vaporization. Of course, we also need the melting point and boiling point of this oxygen. And be sure we need to do this under 1 bar pressure so that we'll be able to get the entropy of oxygen gas in the standard state. What if we are interested in oxygen gas in a non-standard state, let's say 2 bar? Then we can easily calculate the entropy change of the oxygen gas from 1 bar to 2 bars. Given this equation, we can see obviously the molar entropy of a gas is greater than the molar entropy of a liquid than the molar entropy of a solid, because all these 5 terms are positive. The first one is very likely 0 for a perfectly crystalline substance of an element or compound. So our conclusion here regarding temperature: the entropy of a substance always increases as its temperature increases. Now we have a few more things to say about the entropy. A weakly bound matter has greater entropy than a strongly bound one. Why is that? Very simple. Entropy is a measure of the dispersal of energy. It's also a measure of disorder. A weakly bound matter has a higher disorder than a strongly bound one, and also energy is more dispersed in a weakly bound matter. Boltzmann has his own definition of entropy. It's Kb times the logarithm of the number of states accessible to the system. So the entropy of a system increases as the number of possible states the system may adopt increases. For example, when you have a single atom, there's no vibrational modes But if you have a diatomic molecule, there's one possible vibration mode. When you have a triatomic molecule, well, it depends. If you have a linear molecule, then you have 4 vibrational modes. If it's nonlinear, such as water, you have 3 vibrational modes. Each vibrational mode has multiple energy levels. What does that mean? If you have a molecule with more atoms, you have more vibrational modes and more vibrational energy levels, and energy is more dispersed. Therefore, the entropy is higher. For example, ethane has a greater entropy than methane. For noble gases, well, helium, neon, argon. Neither of them has any vibration or rotation, but we can still compare their molar entropy. The heavier atom has higher entropy than the lighter ones. So argon has higher molar entropy than neon. Neon has higher entropy than helium. This is a quantum mechanical behavior, and we're actually talking about the so-called translational entropy here. If we have similar molecules, let's compare this CBr4 versus CF4. They look similar, they have the same number of atoms, and even this Br and this F, they are both halides. Well, in this case, again, heavier molecules have higher entropy. So this tetrabromocarbon has higher molar entropy than this CF4.